This first session, I will probably do a groundwork, setting up the stage for all the follow-up simulation software hands-on trainings, and I think this will be applicable to other softwares as well. Where why simulation is needed in additive manufacturing, we know that it's been a legacy, piece of technology when it comes to aerospace, defense, and semiconductors industry. But when it comes to additive manufacturing, where the complexity is quite huge, and yet the adoption of simulation-based software is limited. But now is the time that this matter has to be taken more seriously, and there's a certain urgency around it, and therefore I will try to make a case in this first half an hour to 45 minutes as to why physics-based simulation are a necessity in additive manufacturing. Like it was mentioned earlier, the course of this course would be starting with my presentation, which is going on right now, followed by an integrated computational platform for end-to-end AM workflow using AM PravaH. That is our two. Followed by installation questions. Many of you people might have installed. Some of you might have problems. So installation and the demo of the software, followed by 4th, 5th, 6th, and 7th hours, where it will be all hands-on training of LPBF or of wire laser additive manufacturing, of using Qs and AI modules of AM PravaH. Followed by the very last hour tomorrow, where we will talk about different visions that we have for this piece of technology, and followed by questions and answers. What are the present developments in the field of additive manufacturing? We all know that AM finds a lot of application in aerospace, biomedical, structural, automotive, and wherever there's a high value industry. There's an organic need for additive manufacturing in those sectors. But a lot of focus is going on right now on new material innovation, exploring different processing methods. So we already know there are a few processing methods, but then there are variations that are coming out. When we talk about new material innovation, a lot of new alloys are being made, especially high strength alloys for aerospace and defense applications. Multiple metals are being welded together. They are being additively manufactured together. The third one is the complexity is something which is which is inherently a good point when it comes to utilizing the full ability of additive manufacturing processes. It gives you functional design, it saves you weight, hence it saves you money as well. So the more complex the part is, the more justified it is to use additive manufacturing. There's a lot of developments or R&D going on, integration with experimental setups like synchrotron X-ray imaging. Synchrotron X-ray imaging, out of many tests that I'm going to talk about later as well, is a very powerful piece of equipment. Unfortunately, there's a limited use of this X-ray imaging machine, owing to various limitations, such as the machines are very limited. Maybe they cost a lot of money. The paperwork surrounding it is quite heavy. So there's a lot of experimental or a lot of development going on how these sort of high performance and high data providing machines can be utilized more in additive manufacturing setup. In situ characterization, where again, this characterization business is a long drawn out process where you print coupons, you send it for printing. Characterization happens using different imaging techniques. Can we reduce that cycle time and try to do it in situ? The last one, which is slightly touching upon the process of simulations, is creating digital twins of the process so that you can reduce a lot of trials and errors that go behind the whole experimentation process and the real production development. I will talk about a few interesting case studies from of course aerospace has to be there. So this is a bleed air leak detect bracket, developed by Lockheed Martin and Oak Ridge National Laboratory in the US. Uh, it was a part of the engine for a fighter plane, and you can see the very complex part on the bottom right of the screen here. Just I hope you will appreciate the complexity of this particular part. And when this part was manufactured additively, the cost and the time, the build time and the cost were both reduced by more than 50% when compared to the traditional methods. So this is a huge saving, not only from the cost point of view, but on the time point of view as well, while maintaining the structural integrity of the part. It's not that you are removing material and hence you are losing on the strength of this material. So these sort of complicated parts using very high performance sort of alloys can be developed, can be printed using 3D printing process. Another industry which is to my surprise is heavily using additive manufacturing is biomedical industry. Recently, there was a case with a friend, and even in tier 2 or tier 3 cities, when you go to a doctor and if you want a tooth replacement for X number of reasons, even in tier 2 and tier 3 cities, the dentist would recommend, would you like a replacement, a 3D printed tooth replacement for your particular tooth? And that has become a possibility, and it has reached the actual end user. So similarly, what we are showing here is a mandible reconstruction using titanium based alloy, using additive manufacturing. And then when you use traditional methods, there are certain ways of doing it. So when you do it using additive manufacturing, the implants are very patient specific. They fit well to the patient's bone structure right away, and there's not a lot of readjustment that is supposed to be done. In fact, one of the very cutting research area that I saw recently at one of the other talks was, when a bone breaks from the middle altogether, then they're trying to find some additively manufactured materials which can replace the actual bone material in between, and that amount of porosity that you need inside that particular additively manufactured bone should be such that it should allow for the nutrient passage from the neighboring bones. So that is a level of complexity that we are reaching. Of course, it reduces the surgical time because the custom fit implant just fits right away. There's no adjustments needed later on. There's no bending involved, and hence the overall patient experience improves. And again, whenever there's complexity, it's a natural choice. And human body is quite complex. Each patient has its own complex of bone structure, body structure, and so additive manufacturing is a organic choice for that industry as well, biomedical industry as well. But again, there has to be. I mean, it's not a as mature of an industry as we can talk about, automotive or defense. So there are certain reasons that why we are lagging behind when it comes to additive manufacturing and complete adoption of this industry, of this technology. And one of the main reasons is lack of technological infrastructure, lack of characterization facility and instrumentation. I already pointed out that characterization and instrumentation is a very necessary part of any additive manufacturing part production, especially on the R&D phase and then also in the production phase. There's lack of skilled personnel, lack of indigenous resources like powders. This is something that most countries all over the world are having problems with. Generating atomized powders using plasma, gas, or water is not a very straightforward process. The technology in itself is quite complicated. Therefore, it becomes important for everyone to investigate if how can they indigenously develop their own powders that are spherical enough. Ignorance of using physics assisted tools for prediction. A certain amount of confusion has been created in the market in the name of simulation softwares that can do additive manufacturing processes. But as we will go through this over the course of next 2 days, our goal would be to make you appreciate that additive manufacturing is a very physics heavy process. You cannot simply ignore the physics and the engineering that goes behind manufacturing these machines, manufacturing these parts, and hence this understanding is quite critical in creating in wider adoption of additive manufacturing across industries. So, of course, some of the solutions, physics informed simulation software to minimize wastage is one, but also to help indigenous growth of technology. For example, powder manufacturing, for example, machine manufacturing. You want to do multiple lasers, you want to do laser beam shaping, you want to try new materials for your own particular applications. All that can be done with the assistance of physics informed simulation software. Preparing material database, the properties associated with materials are still something that are a headache for many additive manufacturing users. Apart from some 10 to 12 standard material properties, it is very difficult to find other ones. Standardization and quality assurance, of course, goes on the legal side and the application side, and global collaborations and networking among universities, among research institutions is something that is very important. Now, I keep saying that simulation has been adopted very well in other industries. So I'll give you an example of Rolls-Royce automotive industry. They and automotive industry has been using these physics assisted simulation software for decades now, probably for 4 decades, and one of the earlier adopters as well. When we talk about engine modeling, Rolls-Royce heavily uses thermomechanical engine modeling. They couple their computational fluid dynamics and structural solvers for coming up with better designs, and they almost are at the verge of creating digital twin for their entire engine. Uh, the assembly and even the layout of the assembly is done virtual. So there's another layer on top of the CFD models where they're not only doing in-depth analysis, in-depth CFD analysis or a simulation of the engine. They're also doing simulations of as to how these will be assembled in real case. Their approach was to use simulation, of course, if they want to understand the thermodynamics and the mechanical strength of the engine. They coupled it with a high performance computer from Intel, and they coupled CFD with the structural simulations. Again, they had to launch it on a high performance computer. They use real time sensor feed for the virtual engine models, and in the end they used virtual reality for actual assembly of these engines on the real cars. And the key impacts are huge. I mean, the run times were reduced by 100 times because your prototyping costs are reduced, you get faster design cycles. Overall thermal structural integration was much faster. Your maintenance was more well understood. It was predictive. You would know in advance when maintenance is needed. Your downtime reduced by 40%, and overall reliability on the product and your own assembly line increased. And when I talk about numbers, they were saving 1.89 million euros just on this single project, and they do probably tens of these projects per year. Uh, so overall, if I were to give you a synopsis of how the simulations are affecting the industry, Rolls-Royce has successfully used simulation, is currently using simulation-driven engineering, and there are thousands of companies using these sort of simulation software. NVIDIA and BMW heavily collaborated to drive the manufacturing of to drive the future of manufacturing by using very realistic digital twins and virtual worlds. SpaceX is using simulations, high performance simulations in their Falcon rockets and Dragon capsules, and 50% increase in throughput just by using simulations. So all in all, this case is well established that when you are using simulations for improving your engines, for improving the aerodynamics, for the flow mechanics around your high performance parts, then why can't we use simulations in manufacturing as well, which are anyways ending up in the same high performing parts. Okay. So simulations, whenever we talk about a new technology, it always starts with academia and on the R&D end first, followed by industry. So I'm going to tell in this particular slide how AM simulations could be useful in academia, starting with the quality of publications. I mean, many high grade journals and publications that are coming out these days inherently require you to not only show experimental results, but also include a much more in-depth understanding of the physics They just don't want you to comment on the observations from the experiment. They also want you to comment on what if scenarios. Uh, they want to comment you on the why these particular observations are coming, and that can be done using these sort of physics assisted simulation software. Uh, it gives complete prediction of the process, complementary to in situ studies. It provides very in-depth 3D information, which is both spatial and temporal in nature. There's LPBF processes, they could be operating at thousands of degrees. And it is very difficult to put any piece of machinery around those high temperatures and really look inside the porosity, inside the melt pools. Uh, and even if you can do that, you can do only as much. You can probably do few experiments in a year. You cannot be doing 100 experiments in a day. It reduces overall expenses on experimentals, on experiments, trials, and errors, and it adds to the value of the researchers with a complete end-to-end physics assisted solution in process modeling and microstructure evolution. Now, when we take this result to academia, the primary goal is money, saving money. The primary goal is saving wastage and reducing the run times. So AM simulations directly impact that. It minimizes the reliance on extensive experiments. It improves the overall throughput of your manufactured parts. It reduces component wastage, reduces better optimizes your process parameters. Let's say there are 100 process parameters that you want to change for a new material. Just imagine the amount of complexity, how many permutations and combinations you will have to go through to really optimize and come to the right set of process parameters. And then also this simulation software, this is a very critical point, and touches upon the collaboration that I earlier talked about. It helps in a smooth transition from something that you have developed in your research lab and takes it to the market in a better manner, because it assists in part qualification and certification as well. So overall, not just academia but industry can also directly benefit for these sort of simulation tools. There are a few myths about simulations. I want to clarify them before moving forward. Uh, Simulations are not a replacement for experiments. They are just a complement to experiments. So let's say you are doing 100 experiments in a year. Uh, Please don't think that simulations are going to remove all 100 experiments. What simulations can do are two things. One, you may still do 100 experiments, but another 1,000 virtual experiments in a simulation software. So total you will end up with 1,100 experiments. Or alternatively, you can do 50 experiments still. Remaining 50 you can do with simulations. And based on the understanding from these simulations, you can devise your experiments in a better manner. But in no scenario we are getting rid of experiments altogether. Uh, Another myth: all simulation softwares do the same thing. No, that is not true. They operate at different levels of accuracy. They use different methodologies, and they have different goals to the customer. Uh, a simulation will always produce a precise, or I would rather say a correct answer to the problem. No, that is not true. Simulation software, because due to the lack of certain properties, lack of process parameters, or just inherent inaccuracies in a simulation software, you may always end up with certain error. But with when as you start moving towards more and more physics informed simulations, these error percentages reduce and end up in the ballpark of human error that you may see in the experiments, because even in experiments there's always a human error or the machine error associated to it. And that could be in the range of single digits, 0 to 10%, something like that. And you can, with the simulations, also reach the same point, given that you are using as accurate simulations equations as possible. Simulators can be computationally fast or computationally slow. I mean, these are both myths. It all depends on what you want. You can run a simulation in 10 minutes, a very high fidelity, very physics informed simulation in 10 minutes, and you can also run the same physics involved informed simulation for 1 week. What changes is how accurately you want to capture that process, and that is in the hands of the user many times. Simulations can tell exactly what will happen. Yes, they can give you a lot of information, but Like I said, it depends on your requirements. If you want everything out of a simulation, then you have to invest accordingly. If you want something, only certain aspects out of a simulation, then you have to invest in a very different manner. Anyone can simulate a system without understanding the domain. That is, again, it goes both ways. It depends on how well the interface of that particular simulation software is made. Some simulation software do not even have an interface, and they can be operated by a handful of people in the entire world. However, some software are very easy to use. They have a nice graphical interface, and they can be used even by the workmen on the floor shop. Just to replace some of these myths, again, whatever I said is summarized here. Simulations can complement experiments, and simulations operate on different methodologies, such as FDM, which is finite difference method, FEM, which is finite element method, and FVM, which is finite volume method. And then for microstructure sort of analysis, there are Monte Carlo, cellular automata, phase field modeling, and all those sorts of things. And like I said, computation time depends on the fidelity of your particular simulation as well. This is sort of an informative slide for those of you who are interested in any sort of simulations. Out of many approaches, there are newer ones as well, but very classical approaches to solve an equation of physics is finite element method, finite volume method, or finite difference method. Specifically, when we talk about the melt pool dynamics sort of problems, or additive manufacturing sort of problems, where you're not only solving the three classical equations, which is conservation of energy, conservation of momentum, and conservation of mass, you're also dealing with phase change. You're dealing with multiple fluids simultaneously. You're dealing with a lot of laser and optical physics, and all this is happening in a very coupled manner. You are dealing with solidification, melting, vaporization, keyhole formation, surface tensions, electromagnetic forces when we talk about wire arc additive manufacturing. So these things can be handled by computational fluid dynamics quite effectively, given that you appropriately modify the equations, append the new equations as are needed for additive manufacturing process. So finite element method, it uses in a very sort of layman terms, they all use some sort of elements. They all discretize your entire volume into smaller volumes. For example, finite volume uses triangles. Finite volume could be using hexahedrals or triangles. Finite difference uses very regular grid points, which is called unstructured meshing is typically not appreciated with finite difference methods. The flexibility of discretization also varies among the three methods. Conservative finite volume methods are very conservative in design. Wherever if you go to finite difference methods, which are used by some commercially available software, they may or may not be conservative. Typically, theoretically speaking, they are not conservative. For example, your mass, your momentum, and energy may not be 100% conserved, because the type of mathematics that goes behind solving these equations varies in finite difference method versus finite volume method. Applications for finite element method, by the nature of their discretization, are they are better suited for structural mechanics. So you'll see some commercial software which are doing thermomechanical stress analysis. They are doing things like deformations, stress problems, residual stresses. So for those sort of problems, finite element methods are useful. When it comes to proper computational fluid dynamics, fluid flow, heat transfer, mass transfer, conservation laws, phase change, finite volume method is very applicable here, especially when you are going to smaller sizes. Your conservation becomes more critical. You can always lose mass. You anyways have microliters of mass in your system, or micro kgs of mass in your system, and if you start losing mass on top of that, you will start seeing the side effects of conservation loss. So finite volume method takes very good care of that. When it comes to finite difference method, it can again handle slightly simplistic problems such as heat conduction, wave propagation, but also used in the CFD industry. So next time When you go ask a CFD or a AM simulation software company as to when you're considering using a particular AM simulation software in your additive manufacturing research, try asking that particular person or that company as to which particular technique they are using. Are you using FEM? Then you know what you can do with FEM. There are certain limitations. If they're using FDM, then you know what they can do. And if they're using FEM, then you know what they can do. So that sort of information should be asked. So that was all on the melt pool dynamics, but a big chunk of additive manufacturing research goes into microstructure simulations, grain morphology, and there are many methods for that also. A Monte Carlo Potts method, CA is cellular automata, and phase field methods. Again, they all try to address the microstructure aspect, but with the increase in accuracy of one method, its performance significantly goes down. So let's talk with phase field method one, which is the rightmost one. It is PDs or the governing equations of microstructure are derived from free energy functional. The time scales are very physical time scales. The real process that is happening, computational costs are very high, not high, they're extremely high. And one of the biggest points of discouragement as to why phase field modeling cannot be used beyond a few microns around the nucleation of the solidification field. Interface accuracy is quite accurate, and this is on paper the most accurate sort of method. But when it comes to real application, industry, or research, uh, the limitations on the computational cost are significantly high to make any real value out of it. Cellular automata and Monte Carlo pots are the two remaining options apart from phase field, which have low to moderate sort of computational cost. Monte Carlo pots uses probabilistic energy minimization, wherever cellular automata uses rule-based local interactions. The interface accuracy is again moderate in both the cases, and ease of implementation is again easy in both the cases. So again, when you go to a vendor and ask them as to how are you predicting your microstructures, they would either tell you Monte Carlo pots, they will tell you cellular automata or phase field. And at that time, you need to evaluate what are your needs, what sort of computational power you have, what are your goals, and based on that, you can select a vendor. So having said that, I'm very happy to introduce AM PravaH, which is going to be the center stage for the next two stage. This particular piece of high fidelity physics based simulation software is the world's first end to end dedicated simulation platform for additive manufacturing. And as we go through this set of presentations, you will see why I call it world's first and why it is end to end. In fact, there's an entire presentation dedicated to that. So currently we are doing laser Boudin wet fusion, we are doing wire laser direct energy deposition, and wire arc additive manufacturing is something that we are seeing amazing results. And we are very soon going to implement this in our regular distribution of the software. In this particular slide itself, I'm sure you will be able to appreciate, the fidelity, how well the physics is captured in all the three processes. In fact, the wire arc additive manufacturing, this is something very new, very close to my heart. So you can see that the droplet dynamics is quite accurately captured. We have not just taken droplet frequency artificially. The droplets are actually and organically developed, created, because they're sitting in an electromagnetic force field, and accordingly, because of that particular arc, and the arc that is created, the energy distribution because of that arc is causing the melting of the powder and creating a melt pool and a bead on top of it. Some of the very salient features, this is, no matter how much I talk about the software, there will always be more to say, but to summarize, uh, the main features, this is multi-phase. What I mean by multi-phase is, most simulation software, in fact all simulation software to the best of my knowledge in the world, are currently operating in one phase or two phase, which means when they're simulating an additive manufacturing process, they are doing the solid alloy, they're simulating the molten alloy, and that's it. But then, for those of you who come from the AM field, would immediately identify that there are two more phases involved which need to be simulated, which is the alloy vapor or the metal vapor. Typically happens after 3000, 3200 Kelvin. And then there's a fourth phase which plays a critical role, which is the shielding gas. Now, when a particular piece of solver does the solid and the molten phase, then you have totally neglected the effects of the vapor phase, which is very critical in forming the keyholes, in giving you the correct information about the pores. The flow of the shielding gas on top also significantly affects the amount of defects you will see in a particular part. Now there are softwares that are doing the vapor phase and the shielding phase using empirical formulation. But when you use empirical formulation, you have completely neglected the real drag, the real recoil pressures, the real sense of compressibility that happens when your vapor leaves your keyhole. So that is the level of fidelity at which we have developed the software, and we are proud to say that to the best. Again, we are proud to say we are world's first complete four-phase simulation software that is trying to capture this whole melt pool dynamics business in its high accuracy. We are multi-physics because we are not only doing computational fluid dynamics, we are doing discrete element modeling for powder bed preparation, which is complete solid mechanics assisted modeling. We are doing laser dynamics. We are doing other sorts of dynamics, which is phase change, and this is all happening in a very coupled manner. We are doing microstructure evolution and and other sorts of physics. We are multi-scale. The reason why it is multi-scale, because we are going all the way from micron scale up to millimeter scale, because we can do multiple tracks. In fact, in one of the presentations later, I think it's on the last day, by one of the eminent speakers, you are going to see that they have successfully done an entire coupon. They have almost printed the real size coupon using, many layers, many tracks on each layer. And so now, while the physics is captured at a micron scale, uh, we are starting to simulate at a millimeter scale, and now with future developments, we'll soon going to start into get into the meter scale as well. The last module is AI, which is quite fantastic. In fact, one of the speakers here might have talked about this. We are doing a lot of simulations and taking that FADA data and feeding it back into our AI module, which helps users in making better decisions about their process parameters, in better optimization, in better decision about some of the properties, material properties, which are completely disappearing from any of the research papers on experimental data. Using all these four sort of modules, or four salient features, we are doing part qualification, material innovation, melt pool dynamics, defect analysis, microstructure and texture information, and finally the mechanical strength of your build part. Okay, so we keep saying that simulations are good, but unfortunately or fortunately, the fact remains it's the money that matters in the end, whether it is academia, whether it is pure research lab, or industry for that matter. Everyone wants to do good work. Someone for producing better parts, someone for producing better research papers, someone for doing genuinely new innovation. But no matter what field you belong to, you always want to keep the costs low and want to do it at the lowest possible cost. So we did a very sort of tentative calculations as to what would a single part take, uh, what would a single part qualification take for a particularly new metal. It would cost you around 6 lakh to 9 lakh rupees, and I will show you what sort of experiments would be included, especially if it's an aerospace or defense sort of uh, part. With AM PravaH, this cost can be reduced significantly, up to 65 to 70% cost can be reduced. And there are some assumptions that are made in presenting these figures. The assumptions are, moderate to high end AM part qualification. So let's say you're going for aerospace, defense, or medical application. We are assuming that you have access to a local lab and testing facility within your office, within your workshop. We are assuming that each test includes associated labor, extensive sample preparation, and high-end equipment use. So we are already included those costs as well in this sort of data analysis. And based on the price of a particular simulation software license, in this case, I'm going to talk about PravaH. It will be amortized over multiple projects, which means the cost of the license will very soon break even after only few such qualification attempts. And this is the cost for a single particular uh, part qualification. There are so many alloys in the market. There are so many process parameters, and you could possibly doing on paper. You should ideally be doing thousands of these experiments and spend the same amount of money every time, but you simply can't. I mean, that is prohibited. So the only way out is to really replace much of the burden on the experiments by using simulations. So let's elaborate a little bit more how this is prepared. So like I said, the estimated cost saving would be 65 to 70% compared to the traditional approach of qualification, part qualification or research. With PravaH, you can save a lot of money. But what tests am I talking about? I'm talking about tensile test, density test, optical microscopy, and so on. And for each of these tests, a tensile test is a relatively cheaper one. They save you, traditionally costs you 25K to 30K, and multiple coupons are tested at the same time. With PravaH, you can save, maybe 15 to 20K on this. And how are you saving? Because it is reducing the amount of destructive samples. Simulations optimize your build, hence you don't have to do that much tensile tests. Moving on to density tests, again you save certain amount compared to the traditional cost, and the trial builds are reduced, hence your density tests are reduced. Optical microscopy, you save by simulating the grain structures in advance, and hence coming out with better builds that require less polishing and etching. When it comes to build test, you're saving money by avoiding failed builds, poor supports, and warping. The next one is quite important: EBSD, SEM, EDS. I mean, material scientists would very well identify the importance of these tests. Uh, these you can have targeted zones where you want to mitigate defects. You can have better understanding of certain zones inside your build part using simulation data, and that's how you can save on these experiments. XRD data, simulations can predict phases, residual stresses, and hence fewer scans are needed. I mean, at the end, you are reducing the number of scans. I mean, that is the final outcome of all these simulation activity. Synchrotron XRD, this is something I talked about earlier. It is rarely used, very less available as well, but quite powerful. Really gives you a lot of information about your melt pool. But pre-selection of regions saves beam time and sample preparation using simulations. X-ray CT, simulations can narrow the scan regions, avoids full volume scans. You don't have to do the entire scan. You can just identify certain problematic zones and only scan those. TEM data, predictive modeling targets high risk zones. Again, you don't have to do for many parts, for the entire parts. You can focus on certain parts only. Fatigue and creep tests, virtual life modeling, filters suboptimal builds, and then last one is the fractography. Again, you can have a focused analysis of predictive crack zones. So this particular graph, I will also share maybe by the end of tomorrow, so that you can have some sort of reference as to what you are really investing in your simulations. Okay. So this is a summary again, what each of these tests are doing and how you are really saving cost and improving your research using simulations for, in a, one-on-one comparison with that particular test versus the simulation. Okay. So what is the benefit of using PravaH? End-to-end simulation solution. We are cutting down 67% of the cost. The chance of failure is reducing down to 10%, saves experimental trials and characterization, and it is going to emerge. We are committed to making it a digital twin for AM process, and just appreciate the scales at which we are operating. We are going all the way, or the process chain. not the scales, but the additive manufacturing chain starts from powder manufacturing, and it goes all the way to the part scale, the real build. So we are starting with the atomization process itself, where powder can be manufactured. It's a supersonic inert gas atomizer. Then that powder is used to prepare a powder bed. We are using discrete element method, very accurate solid dynamics, solid mechanics, collision mechanics to simulate these sort of powder distribution, followed by computational fluid dynamics, which is the melt pool dynamics, followed by Monte Carlo process simulation to predict the microstructures, the grain morphology, and then followed by finite element methods to do part scale simulations. So basically, everything, different techniques at different scales that are applicable and most suitable are captured in this particular piece of software. We are very happy to have some very good users of our software. Some of them will be talking about it as well, and hope to see a lot of good work coming out of the software and exploring those dimensions of the software which even we have not explored yet. And we'll all try to showcase, cover, because there's just so much to cover. So we are all experts in different aspects of the software. Thank you.